We're still talking about conditional independence. We're going to talk about conditional independence a lot. Is there a relationship between, if you go to school, elementary school, K through 8, is there a relationship between the shoe size of people and their math ability? If I told you somebody's shoe size, will you be able to tell me something about their math ability? Yeah? Some people say yes, some people say no. Like, if you think there's a relationship, is it positive or negative? Bigger shoe size corresponds to higher math ability or higher? Okay. So when you have a child, remember, when you go to the store, get them a shoe that's 2 sizes bigger. It will move the... Why is that funny? Okay, it's correlation, not causation. But where does the correlation come from? Yeah, bigger shoe size is correlated with higher math ability in K through 8 school. Shoe size. Call it math level. I don't want to confuse that with math talent, but math level. How much math they know. So this will be shoe, and this will be math, and they're not independent, right? What about the grade level? Grade level affects the shoe size, and it also affects the math level. If you are in 7th grade, you typically have a larger shoe size than somebody in 2nd grade, and you typically know more math than somebody in 2nd grade, I would hope. Shoe size is independent of math level given the grade level, conditioned on the grade level. It's not always the case, but it's usually the case that if you find all the common causes for something, conditioned on these common causes, they become independent. So in our example of 2 tests, we had test 1 and test 2. And typically test 1 and test 2 are not independent. But when you start thinking about what are all the reasons for errors in the tests, we came up with a whole bunch of them. Lab, technician, genes, things having to do with the individual. Either individual or patient. Once you condition on all of these together, maybe these are independent. Or maybe they're not. Maybe they are less dependent than before, but they may still be somewhat dependent. Dependency could be measured, for example, within mutual information. Remember that independence corresponds to 0 mutual information. So conditional independence corresponds to 0 conditional mutual information. And if you collect a lot of data and you pair together the results of 2 successive tests where all of these are fixed, and then you ask yourself, what is the mutual information between T1 and T2 conditioned on all of these? Lab, technician, genes, patient, or patient includes genes. So this number might be 0 or close enough to 0 given your finite sample size, or it might not be. What would be the explanation if it's not close to 0? Yes, we left out some factors. Maybe the day of week. Right? Maybe there are more errors on Mondays. This is something scientists do all the time. And data scientists think of themselves as scientists. They should know how to do that too. Question?
What's the logical explanation between S not being independent of M?
I'm sorry, what's the what?
Why is S not independent of the structure M?
Why is S not independent of M? Okay. Why is a shoe size not independent of math level? Yes? Suppose you draw a scattergram of shoe sizes versus math level in a school in the US or anywhere. Shoe size math level, well, it's already written here, math level. You take all the kids in the school, it's a school from K through 8, and you put 1 point for every child in the school based on their math level and their shoe size. Focus for a moment on the kids in kindergarten. The shoe sizes will vary around here, and the math level will vary around here, right? Kids in first grade, the shoe sizes might be here and the math level might be here, and so forth. I'm not suggesting it will be nice blocks, but it will clearly lie along this diagonal. There would be some overlap. So if you look at this picture, clearly there's correlation, right? You could plug it into the correlation thing and figure out a correlation coefficient. It's very clear. But if you condition on the grade level, that means paint all the kids in kindergarten a single color, and then this is a different single color, and every grade is a different color, and ask about correlation within each color. That's what conditional independence is. And the answer there, we expect to not be related to shoe size. It might be. There may still be some residual correlation, some residual dependence left, because it could be that within grade 5, there are kids of different ages, and that the older kids tend to do better, maybe. Maybe not. But clearly the most dramatic relationship is mediated by the grade level. Okay. Any other questions or comments about Bayes learning, likelihood, prior? So the kind of Bayes that we've done until now, we focused on how to use the Bayes apparatus. We were given priors and likelihoods. I gave you the likelihood function as a table of 2 by 2. I gave you the prior. We discussed where they come from. If you're going to do Bayes learning, that means learning the parameters of the likelihood and sometimes of the prior. So you might be surprised to think of why do we learn parameters of the prior if prior is supposed to be something that comes before. And the answer, you'd be right. Usually in a normal setup, you come up with your own prior from your prior belief or knowledge. And then you use the data that you have to learn the likelihood function. But sometimes you may learn the prior from other related data that you believe is related. And sometimes we might even cheat and use the training data itself to estimate maybe just 1 or 2 parameters of the prior. This is called an empirical Bayes approach. Empirical Bayes is not truly Bayes. A true Bayesian will not use empirical Bayes. Empirical Bayes says do what a normal Bayesian does, but allow yourself to estimate just a handful of hyperparameters from the data as a whole. Okay, so this goes by the term empirical Bayes. But let's go to the general case of learning a classifier from a lot of data, a lot of features. So our goal is to learn a function from many covariates, call them A1 through AP, into some y. It's a stochastic function. It might produce different y's with the same inputs. But the important thing here is that the p is large. I could use the notation used in the slides. Maybe it'll be easier. I'll use n. Just statisticians like to use p for number of covariates, but let's make it n. Be easier to read Mitchell's slides and maybe others. We'll assume that y is categorical. Namely, we're doing classification. We have a lot of training data for this, meaning we have an A11, A1n, A21 through A2n, all the way to A, say, M1 through AMN. That means we have M different data points, and every data point consists of an array of the attribute values and the correct value, the label, Y1 through YM. So far, this is very similar to the setting for regression, except we're using classification, not regression. We might simplify further and say that y is binary, but we don't have to. And sometimes we will talk about the attributes as being binary, but again, they don't have to be. For now, we'll keep them whatever. We're looking for the map solution. So given a new input, our y map, maximum posterior, as a function of the individual attribute values, is going to be the one that maximizes what label do I use for the categories? I use V, which is again what Mitchell uses. So V would be the set of all possible outputs, all possible labels, and small v would be one of them. It'll be the one that maximizes the probability of V given the attributes. I use the language of maximum posterior. It's not that I have a prior over hypothesis here. What I have instead is a prior over the labels. So I'm just using Bayes' formula with the same mathematical idea, but a different setup. It's not a choice from hypotheses. You can think about it as, you can think about it as if they were hypotheses, but I think a simpler way to think about it is there will be a prior over the labels. Some labels are more likely than others. And I'm trying to determine the most likely label given the attributes. I will write this over V. Again, I will use Bayes' rule now to flip the dependence of the label on the attributes, flip it to attributes given the label. So this would be P of a label times P of attributes, A1 through AN, given the label, divided by P of the attributes. I'll get rid of this. I just use Bayes' formula, which you can apply to any, any two sets of random variables. Just flip them over. And here the usual trick is when you do argmax and you do that flipping over, the denominator is not influenced by the argmax, so we can cross it out. So now we get to interpret what these are. This is typically what we call the prior. In this case, it's a prior over the different possible labels. It will capture the notion that some labels are inherently found more often than others. And this is corresponding to the likelihood. This is the probability for a given label of capturing of the example having specifically these set of values. So remember, lowercase a is a value, uppercase A is the random variable. Now comes the hard part. Now I need to learn the value of these from data, from training data, from the training that I have there. So I'm going to start by reminding myself that these are going to be estimates. The universal notation in statistics for reminding yourself that this is an estimate is putting a hat over the probability. It means it's not the true probability, it's an estimate of that probability. Some estimate of the probability. How do I estimate this? Well, given that I have this data through A1, AM1, I have this matrix and this vector. How would you estimate P of V from this data? You're given this data, M is very large, N is very large.
Count the frequency of how many
Count the frequency of how many times a particular V occurred in my training data and divided by the total number of training examples. Yep, so that would be a reasonable thing to do. We will call it count of V. How many times V occurred in this column? Divide by the total number of training examples that we have, which is M. Is that the right value? Is that the true probability of V? No. Is it an estimate? Is it a good estimate?
If the sample size is large.
If the sample size is large, so one condition is this has to be large. How large? Let's say it's 1 million. Is that a good estimate then? Depends. What does it depend on?
Your data, I guess.
The data? I'm sorry?
It depends on the population, how large the population.
Well, population is going to be 1 million. William?
It also depends on the true probability. If that's very small, like if it's 1 in a billion, you get some label, and maybe you have 0 in your current, so you have a million.
Right, so I can modify that and say that if the number here is very small, I should be wary. If the number here is 0, I should be very wary. Just because something occurred 0 times doesn't mean that its probability is 0. It could occur next. But even if it occurred here once, if something occurred once out of 1 million, then 1 in a million is an estimate, not a bad estimate, but not a great estimate either. It could easily, the true probability could easily be 5 out of 1 million, or 1/10 of a million, or 1 over 10 million. If the number here is 5 or larger, it starts being a reasonable estimate. So I will call this my relative frequency estimate. And as you know by now from the example we did, binomial, if you think about it as a binomial distribution, is it V or is it not V? This is also the maximum likelihood estimate. So I'll call it relative frequency. I'll also call it the maximum likelihood estimate. It's important to know that there could be other estimates, and they might have somewhat better properties. But this is, for this case, this is a fairly simple case because the number of labels that we expect in this kind of classification is small. It could be 2, it could be 5, it could be 10, it could be 100. And the number of examples we have is going to be much large. So typically, M, the number of examples, is going to be much larger than the size of the number of labels. As long as that's the case, this is usually not going to be a problem. You just have to watch out for rare labels, for rare cases. And if they occurred only 0, 1, or 2, or 3 times, we'll need to think about what to do, but it typically won't happen. And now let's look. So this is okay, easy. Easy. But now let's look at this. Let's try to apply the same methodology to estimating this thing. So we're looking for an estimate of the probability of A1 being a particular A1 all the way to AN being a particular AN, given that V, or Y as they call it, is a particular V. And we could use relative frequency, or we can try to use relative frequency here. That would be count how many times in my training data I saw this particular combination of A1 through AN and V, divided by count of how many times I saw V. This is a relative frequency estimator for this part of the equation. Is it a reasonable estimator? So let's put specific numbers down. Let's say that M is 1,000,000. I have 1,000,000 training examples. And let's say that N, V, let's say V is just 2. 2 labels, binary classification, yes or no. And let us say that N is 100. So you have 100 attributes, and let me simplify it further. Let's say the attributes are binary. So you have 100 binary attributes and a binary output, and you have 1,000,000 training examples. That's a very reasonable setting. You're trying to decide whether to give a loan to somebody, and their personal information is expressed in terms of 100 attributes. That sounds reasonable. 100 binary attributes. What about this estimator? Do you like it? Do you dislike it? Are you indifferent? Yeah?
Well, if we're looking for the count of A1 to AN and some particular V for n equals 100, there's, what, 2 to the 101 different possibilities?
Mm-hmm.
So we might not get very many of those, so it could be a poor estimate.
So what you're saying is that the number of possible combinations here is so large, specifically, as you pointed out, 2 to the 101 possibilities, combinations, which means that when you come to classify a new test example, chances are the particular combination of attributes has not been seen before. That's not necessarily true. Even though there are 100 attributes, it's possible that things keep occurring in groups. But it's certainly a very common, a very likely occurrence that different examples would have different combination of these 100 covariates. Which means that when you come to classify a new test example, most of the time you'll find 0 here over something. Is that a bad thing? Yeah? I don't see enough heads nodding. Yeah, it's a bad thing. These are not the true probabilities. By accepting this as your estimate, you're basically killing this part. This becomes 0. And it may very well be 0 for all the labels. So you won't get an answer out of this. What we want is ideally to estimate a better probability for each such combination. How many parameters would that require? 100 binary attributes, a binary output. How many probabilities will be involved? Suppose we could somehow get the right values. How many parameters would there be? There'll be as many parameters as there are expressions of this form, probability of A1, AN, and V, where these I's could be the 0, 1, 0, 1, 0, 1, all the way including the label 0, 1. In other words, they are on the order of 2 to the n plus 1 parameters. This probability function or form is called the joint probability function. The joint probability function of multiple random variables expresses the probability of every combination of these random variables. The joint probability function would have to have as many numbers as there are combinations, namely exponential in the number of random variables in it. And this is where our problem is. To truly solve this problem in the Bayesian way, we will need to estimate an exponential number of parameters. And we usually don't have enough data for that. We have m data, we have 2 to the n, roughly, parameters. That's where we get stuck. What do we do? When you don't have enough data to support your parameters, what do you do? Yeah. Make assumptions, thank you. That's what I wanted you to say, to all say. Make assumptions. And what assumptions should we make? Yeah?
You could start with only one attribute being the factor, being the most important factor in the variables, and then we can expand that to using 2 and then kind of probabilities as
Interesting suggestion that we go step by step. We figure that one attribute is the most important and rely on it, and then go to another attribute based on that. That sounds like a decision tree. Very reasonable way to go about this, absolutely. Yeah?
If we assume that they're independent, then a joint probability just becomes a product of the marginals, and so we can calculate joint probability without having to specifically.
If we assume that the attributes are independent of each other, then we can factor this joint probability into a product of marginals. And then we only have to estimate the probability of the marginals. How many marginals do we have? Marginals means probability of just individual attributes. We have on the order of n. So that's a win. All right, so let me try to run with this, but let's make the problem very concrete. Suppose what we're trying to do is to estimate, is to learn the topic of a document. Let's say there are only 2 topics, sports and foreign affairs. You have 1 million documents to train on. Half of them roughly are about sports, half of them are about foreign affairs, and they're all labeled. Our attributes are going to be the occurrence of specific words in the document. So documents can have thousands of words, so there could be thousands of attributes. And a word like referee, let's just talk about the attributes as being binary. So either a referee occurred 1 or more times or it didn't occur. If it occurred, you think it's much more likely to occur in a sports document than a foreign affairs document. And a word like ambassador is maybe occur in foreign affairs. So far, this is what you're suggesting. Now, you're asking me to make the assumption that the attributes are independent of each other. So if I see the word ambassador, it doesn't change the probability that I will also see the word treaty. Not a great assumption, right? Or if I see the word referee, it doesn't change the probability that I see the word basketball. I think it does. I think it does. If I see the word referee, intuitively I know it's about sports. So the probability of basketball should jump by a factor of 2, right? Because now I ruled out all the documents that don't tend to have any basketball in them. So the assumption of independence between the attributes, in this case, is not a reasonable one. Somebody had a suggestion, improvement? Yeah?
So the issue when we were trying to estimate the instance, the probability of using counts was that like it's very unlikely to get exactly that combination. But could we just relax that and say like, could we count the number of ways we get like almost that combination?
Like, what do you mean by that combination? Like,
So like,
combine them?
it's likely that we won't see exactly like exactly A1
Uh-huh.
with B. But could we like say include all the combinations where maybe it's that but like one different or two different or like up to like some number different?
Yes, you can. Let me repeat that. That's a very reasonable suggestion. Our problem, our sparsity, our problem of not being able to estimate so many parameters comes from the fact that we insist on making an exact distinction for all the attributes. In other words, if 99 of the attributes are the same of two test examples and one of them is different, we treat them as completely different. And your point is, we don't have to treat them as completely different. We can kind of look at the difference between, we look at the test example and we see what training example doesn't match it exactly, but is similar to it. You invented K nearest neighbor. We will talk about it in a few weeks. Very reasonable thing to do. Another thing we can do is if we have reason to think that the attributes affect the answer in a similar way, we can look at combinations as in linear addition, combination of attributes. So kind of reduce the number of attributes that you have by saying it's going to be this attribute plus this one plus this one plus this one is one attribute. And then it does effectively the same thing if it takes, or similar thing, takes combinations of attributes and treats them as one. This would lead more to like a linear regression kind of method. So yeah, there are many things we can do. We don't have to go the path we're pushing now. Question?
Aren't we also overfitting to the data by what we're trying to find? Because if you're trying to find a particular sample data from A1 to AN, that's dependent on your data. That's very dependent on your data, right? So your maximum.
I'm not sure I understand what you're saying. Are you saying that we selected which attributes are important by looking at the data?
Yeah, I guess, because it depends on your MAP estimate would depend on your data. And if you're looking at particular attributes and not like a subset of attributes, if you look at all the attributes, like a particular, like all the attributes and the values that
I see. Okay. Very good point again. This has to do with how we represent our problem. So you're saying that we looked at the data and then we said a priori that anything that shows up in the data is an attribute, right? And in that sense, we're overfitting to the data. So this is actually very relevant in the example we just used of documents. We talk about each possible word in the dictionary being an attribute. Referee, basketball, ambassador, and so forth. But did we really go out and get a dictionary? Or did we just use the words that occurred in our training data as a substitute? If we use the words that occurred in our training data, we are arguably overfitting, maybe in the sense that words that are happen to not be in our training data are outside of our calculation. Possibly, yeah. Yeah?
I would argue that you could go a step further and take all the words that were in your training data and then trim out like 90% of them. Like it's 50% likely they'd be in one type of document or another type, and just say, okay, we just don't even care about those because they don't tend to push us towards either document, and just get rid of those attributes altogether.
I think it's a very fair thing to do. Let me repeat that. Our problem is the number of attributes that we have relative to the amount of data. So this is another way of reducing the number of attributes we have by pre-processing the training data and selecting only words that seem to be more frequent, significantly more frequent in one corpus than in the other. I think in principle it's a good idea. Let me tell you something about language that actually makes it not such a good idea. Language is full of rare events. Rare events happen all the time. And therefore, it's a funny thing to say, right? Which is why I said it. But rare events are frequent in language. What I mean by that is that there are many, many, many rare events in language, rare words, for example. And as you read a normal document, about every second or third word is a rare word. It's a word that happens once in a blue moon. So if you do that, you would still end up with a reasonable classifier, but you will actually be throwing away information. Now, if you throw away only words that occurred exactly the same frequency in both categories, then it won't change the result. That is true.
I guess I'm saying don't throw away words that are necessarily rare, but like throw away and, throw away the.
Yeah.
Right? Throw away words that are frequent and, well, not even frequent, but throw away words that are equally frequent in both corpuses.
These are called stop words. And yeah, that helps if you're trying to minimize the amount of processing or amount of space, which these days we rarely worry about. But yeah, you could do that. So you can assume that the word the occurs equally often in both corpora, and you might be wrong. It depends on the style. So my favorite example is I had a student more than 10 years ago who was working on clustering of documents, and there was one document that stood out as a really outlier with regard to the number of the in it. So the word the is about 5% of the English written language. Every 20th word on average is the. That's pretty standard in most genres of written English. And she had this document that had 10% the, and it was clear to us that something is wrong. We looked at the document. It was a translation from Arabic. And not just from Arabic, it was translation from very formal speech that the Iraqi ambassador to the UN gave on the eve of the first Gulf War. And it was full of formalities like the resolution of the Security Council of the United Nations upsets the government of the free people of Iraq and so forth. And the reason it deviated is because in Arabic, the is not a separate word, it's a prefix. And it is much more common in the language than it is in English. So if you translate it not as a native English speaker, but just literally, you will get a lot of the. So sometimes you will find differences due to style. But yeah, that point is well taken. Yes?
Assume that even a document is about a sports category, the probability of the referee and the probability of a goal are independent.
Okay, so you're going back to the suggestion about independence. And I claim that referee and basketball are not independent, because once you see one, you kind of know that you're probably in a sports document, and therefore you're going to see basketball more likely than before you knew that. But you're saying that within the sports documents, once you see referee, it doesn't make basketball any more likely. Is that a reasonable assumption? More reasonable than the previous assumption. Okay, so let's adopt that. This is called conditional independence. Happens to be what I talked about a minute ago. All right, so we're going to make the assumption of conditional independence. Conditional independence is actually not a single assumption. You need to say what is independent of what, conditioned on what. So there are lots of conditional independence assumptions. Some of them are more reasonable than others. We're going to start by making this kind of assumption, that AI is conditionally independent of AJ, conditioned on the label V. For some reason I called it Y. What do you guys like better, V or Y? Y? All right. So I need to change it here everywhere from V to Y. It's too much work. Okay, Y. Hopefully you know what I mean. In our example is a topic. So we have only two topics, sports and foreign affairs, but you can generalize it to 100 topics. And what this is saying is that the attributes of the document, the values are independent of each other within each topic. It does not mean that they are independent without this. Is it a good assumption? Sometimes it is, sometimes it isn't. Most of the time it's not. Most things in the world, especially in the real natural world, they're not independent. You condition them, they become a little bit more independent, but they're still not completely independent. It's a question of how reasonable the assumption is versus how desperate you are to make it, versus how much data you have and so forth. Actually, we're going to make a stronger assumption than this, because this is as strong as it looks, and this is for every I and J. As strong as it looks, it's actually not as strong as it could be. So imagine 3 attributes, A1, A2, and A3. And just in our classic example, this is a random flip of a coin, this is a random flip of a coin, and this is the XOR of the two. This is A1 or A2. A1 is a Bernoulli with a half, and A2 is a Bernoulli with a half. Now, you can easily verify that any 2 of them are independent. Okay, any 2 are independent, meaning switching in your mind to information theory, if you know the value of one of them, it doesn't tell you anything about the value of any of the other 2. Any pair that you have, the mutual information between the pair is 0. But if you know 2 of them, you do know the third. So the 3 are not independent. I'm going to make a stronger assumption. I'm going to make the assumption that any subset of the AIs, I1 through AI, all right, I'll just write it in words. Any subset is independent of any other subset conditioned on the label. This is a much stronger assumption. But usually you will see in the literature, you will see this described, but it's actually not the only assumption being made. All right, I will make this assumption, and this would allow me to factor my estimate of A1 through AN given V into a product of estimates of AI given V. This is the crux. This is the reason I made this assumption. This is not exact. This is an estimate based on this assumption. How many parameters do I need to estimate now? These are all estimates, right? How many parameters do I need to estimate now? Order n, actually it's n times the number of values I have here, which in some of the examples I said was binary, so there will be 2, but in a more general case it would be number of labels. And if these AIs are not binary, then it won't be n, right? If every one of these have 10 possible values, then I have to estimate 10 parameters with 9 degrees of freedom for each one of them. But in general, more general than this, it's linear in the number of covariates. This is the crux of this method, which is called the naive Bayes method. Terrible name, stupid name. Probably, I don't know who invented it. I don't want to even speculate. The only relationship it has to Bayes is that it uses Bayes' formula. Okay. We all use Bayes' formula. The naive word is maybe the right one, but there's so many ways of being naive. It doesn't really capture. I'm a big stickler for names. I want the name to be exactly the right thing, convey the message. So if you can help me come up with a better name for it, I will be grateful. Nobody else would care because it's already been around for 40 years. But what would you call it? We would call it the independence of covariates, conditional independence of covariance assumption model, whatever. the crux of the naive Bayes method is reducing the number of parameters of the model from exponential in the number of covariates to linear in the number of covariates. And the way we do it is by making very strong conditional independence assumptions. Conditioned on the label, we say that all of these are independent of each other. I'm going to draw a graph that corresponds to the naive Bayes assumption. We'll talk about how to read these graphs in general later, but for now I just want to put it here. Here's the label, y, and here are the covariates, A1, A2, AN. We'll come back to this graph. This captures this assumption. It says that when you condition on y, all of these are independent of each other. Just like when you condition on grade level, shoe size and math are independent of each other. All right, so we overcame the biggest hurdle we had, which is reducing the number of parameters. Now we only need to worry about estimating things that look like this. There's still a bit of a worry there. We're going to use the relative frequency estimator. We're going to start with that, which is a reasonable way to start. The relative frequency estimator is also the maximum likelihood estimator. P hat relative frequency of, let's say AI given V is the count of AI of how many times AI is a particular value AI and V is a particular value V divided by the count of how many times V is a particular value V. Sometimes I don't bother writing the name of the random variable here. Right, when I wrote somewhere else here, count of V, this is equivalent, right, to how many times the random variable big V takes on the value small v. Anyway, this means in practice, go to your training data, count this. You already counted that before, so that's easy. How many documents are in this type, for example, this label? And here, you have a smaller number. How many documents are of this type and this attribute had this value? For example, referee showed up or didn't show up, or basketball showed up but didn't show up. Question?
Make the y
Make the y.
one y there and then one y there.
Yeah, no, I'm totally with you. Like here? Yeah. No. It's for future generations. No. I'm totally with you. I think a notation should be just right. There are many ways of misunderstanding. So, all right. So now we have this problem, and it's still a problem because with 100 attributes and an unknown number of topics, you may very well still have situations, then they may not be the majority now, but you may very well have situations where that particular combination of attribute value and label value never occurred. So what do we do if you get 0 over, 50,000? The relative frequency estimator would say 0. But we rely very strongly on these estimates. So if even one of them is 0, this is a product. The entire product would be 0. And if the entire product is 0, did I write it here? If this entire product is 0, then this whole thing is 0. Which means it's enough for one attribute to be new in this label, new under this label, to show up for the first time under this label for one attribute value, for our naive Bayes algorithm to rule out that label completely. And that happens too often for us to be willing to tolerate. Question?
Oh, no, I have to see like a way to fix it. Maybe?
Okay, a way to fix it. How would you fix it?
Can we like assume like non-zero probability and give it like if you get a zero, just give it like a small epsilon.
Yep. So way to fix it is just don't allow zeros. If something would normally get a zero, convert it into, instead of 0, so this is 0, convert it into some kind of epsilon. Like, what would you like, 0.001? Okay. What do you think? Good, bad, ugly? Come.
The probability should depend on the size of because 0.001 could be relatively large depending on how large your data set is.
Good point. If I chose 0.001, this is as if I claim that it occurred 50 times. And that's kind of unfair, because if another attribute occurred 20 times, now you're playing favorites, okay, so we want it to depend on the size of the corpus, yeah?
Could you repeat what happens when without 0? Like, why is that?
So the suggestion is 0 is not good because it's going to kill that hypothesis completely. The suggestion was replace a 0 with some small number, fixed small number. The comment or request for improvement was, well, that number should be proportional to how big this number is, because if it's not, in this particular case, this is equivalent to claiming that it appeared 50 times. Another attribute will have occurred 3 times, and we would be 3 over 50,000, and this one is the equivalent to 50 over 50,000. It's kind of not fair. It didn't occur at all. I say not fair, but what I really mean is it's inconsistent. William?
You could pretend that we have like a single example for every possible example that we see. So we have like an extra n times b example so that every example is from.
Okay, so this is called the Laplace method, and the idea is you add one pseudo count, fake count, to every attribute under every condition. So instead of it being 50 over 0 over 50,000, it becomes 1 over 50,001. Now we need to add 1 for every possible what we have here. For every possible attribute value combination. So let's look at the specific case of a fixed value, for a fixed v. We have a count of AI. And let's assume also binary features. I'm going to pretend that my attribute AI I did something wrong here. All right, let's develop the Laplace method separate from naive Bayes, and then I'll tell you what my problem is. So what we're trying to do is smooth. Smoothing an estimator means practically, most of the time it means just moving it away from 0. A more general view of smoothing is making the estimator less subject to variations in the sample that it's based on. That means reduce the variance of an estimator. So the generic term, the generic explanation for smoothing is reducing variance. What it means here is reducing the most extreme values, with 0 considered a very extreme value. So we're looking at one particular form of smoothing, which is Laplace smoothing, also known as ED1. And the idea is you're looking to estimate distribution of a multinomial with, say, k possible values from 1 to k. Typically, you would estimate the probability of I, the relative frequency of I would be the count of I divided by overall the amount of training data you have. So you would take your training data and you'd throw it into buckets here. These are the I buckets. I goes from 1 to k. This n is the sum of the counts. This is before smoothing. And now you're concerned that some of the buckets might be empty. And you don't want to use a 0 estimate. So the idea is you add, I'll put it as a plus, a pseudo count. So the dots are the real counts and the pluses are pseudo counts, which means you add here the pseudo count of 1. And because you do that, it's as if you, before you started filling the buckets, you put in the individual items. To normalize it, the denominator should have k. 1 for each category. Let's talk about this context for now. I'll come back to naive Bayes in a minute and tell you why I got stuck. What do you think about this method? Yeah?
What if k is significantly larger?
Yeah. So what if k is significantly larger than n? If k is significantly larger than n, that means that most of the buckets are empty, right? So most buckets will get 1 count, and the probability estimate would be 1 over n plus k. And some buckets might have 1 count originally, so now they'll have 2. So that's a pretty strong, it's a good point. You made a pretty strong assumption that they are kind of close to uniform. The question is, can you make a better assumption?
Couldn't you just add a tenth of a count to each bucket?
Yes. Can you add a tenth of a count to each bucket? The answer is yes. So I was expecting we would start in the opposite direction. Can you add more than 1 count? Why 1? Why not 2? Why not 3? And the answer is you can actually add any number of pseudo counts. It would have a slightly different impact, and you can add a fraction of a count. And in your case, you might want to add a fraction of a count. So let me change this. Instead of it being 1, it would be, what letter have we not abused today? Epsilon? Well, epsilon implies small. I don't want to imply small. U, all right. U, and now means this has to be k times u. And now u is our knob. We can make it larger or smaller. What effect would that have? Let's first dial it all the way up. U very, very large. Really, really large. What do you get? Huh?
You start overstating the value of zeros and understating the value of other values.
Okay, as u goes to infinity, what happens to this distribution? It moves towards uniform, right? As u goes the other direction to 0, what happens to this distribution? As long as it doesn't hit 0 exactly, the distribution is somewhat smooth. It does not have zeros. But what does it look like? It looks very, very much like the original relative frequency, which I should not write here anymore. This is Laplace. Or pseudocount. Pseudocount. Count. As the pseudocount knob is near 0, the distribution looks more and more like the original distribution of the data, right? Except instead of 0, you have a little epsilon that you've asked for.
So wouldn't you want KU to be some like fixed percentage of n? Like I would think you want KU to be like a tenth of what n is, or 15% of what n is, you know? So that KU scales with n, and then your knob is just guessing how much is due to the pseudocount from the original.
The suggestion is to make this scale with n. This, to remind you, is the pseudo counts, the fake counts, the amount we're using to smooth, and it's applied uniformly to all buckets. It pushes us towards a uniform distribution. This is what comes from the data. The suggestion is that we make this a fixed fraction of this. Do you like the suggestion? I see one yes.
I guess I'm saying that should be a knob, right? The fraction should be fixed, but the fraction should be the knob that you're adjusting.
Well, if you're saying that k times u should be a knob, that's the same as saying that u is a knob, because k is not your choice. It's fixed with the problem.
Yeah, that's true.
But let me take your question anyway. What do you think about making k times u a fixed fraction of n? You don't like that. Why?
It's a big guess.
I'm sorry?
I was just guessing. Mainly because if it's a fixed fraction of n, shouldn't it be dependent on our data and how many points we have instead of being a fractional constant every time?
So you're suggesting it shouldn't be a constant fraction, but something else that depends on the data. So let me object to the idea of, maybe that's not what you suggested, object to it being a fraction, a fixed fraction. If it is a fixed fraction, then if I one day become very rich and have a tremendous amount of data, it's going to be a burden on me. It's going to distort reality. If I have so much data that I don't need smoothing, that there's no zero anywhere, then it's going to push me significantly towards the uniform. Not completely all the way, but it's going to be a significant push towards the uniform. And I don't want the uniform. I have enough data to make distinctions. So what I want is a method of smoothing that is helpful when I have very little data. But as I have more and more data, I want to be able to rely on my data to paint the picture and not distort it. So from that, I take that this should be a diminishing fraction of this. How diminishing? You know, you can argue with me. But it should diminish in the sense that as this goes to infinity, this should go to infinity much more slowly, even if it goes to infinity at all. Suggestions?
I was just suggesting you do 1 by, so you basically add one sample to n, and your pseudo count you update by like 1 by n.
Say it again.
So you basically choose 1 by k, or either 1 by k or 1 by n, I guess, and then choose that as your u.
1 over n as your what?
As u.
As u. Okay, if you use 1 over n, so this is kn, that will satisfy my condition that it will go to. Let me tell you something about this, this particular smoother. It has actually a very interesting Bayesian interpretation. Let me first give you the hand waving, and then I'll give you the terminology for it. The hand waving is that it determines a balance between your prior notion of what you think the distribution should be and what the data says. By putting 1 in each bucket, you're saying that you have a prior notion of uniformity. You don't have to put 1 in each bucket. You could put 5 in one bucket and 3 in another bucket and 1 and 0.2 in another bucket, right? You don't have to put the same value everywhere. By putting the same value everywhere, you are effectively pushing the solution towards uniform. And then as more data comes in, the solution moves away from the uniform towards the relative frequency solution. So another way of saying it is not that you're pushing it towards uniform, is that you're starting from a uniform. So imagine that you put the pseudo-counts in first before the real data comes in. You put a pseudo-counts in, one in each bucket, you get a uniform distribution. Now the data starts arriving, and it starts changing the distribution away from uniform. So you can think about it as a starting point. It's a starting point for your distribution, and the starting point does not have to be uniform. Second thing, even if you agree that the starting point should be uniform, if you want the starting point to be uniform, you have a choice. You can put 1 in each bucket before the real data arrives, or you can put 5 in each bucket. What's the difference? What's the impact of that choice? In both cases, you're starting from uniform and then allowing the data to change away from the uniform. In which case will the data move you away from the uniform faster? When you have 1. So suppose you didn't put 1, but you put 1,000 pseudo-counts in every bucket. What does this correspond to in terms of an assumption?
Very strong prior.
Very strong prior. It corresponds to you feeling pretty strongly that it should be pretty darn close to uniform. And it'll take a lot of data to convince you otherwise. And the opposite is if you go down below 1 to 0.5 or 0.1 or 0.01, you're also starting with a uniform prior, but with a very little conviction. You're saying, yeah, I'll start with uniform, but I'm easily swayed in either direction, whatever data says. So the choice of which counts to put in which buckets, how many, and how to put them, correspond to effectively a prior. And that prior is called the Dirichlet prior. It is more or less the pseudo-count method. Slight variation. It's not the Dirichlet prior, is map applied to the Dirichlet prior results effectively in the pseudo-count method. So if you started with the Dirichlet prior, which is a very well-known and well-used family of priors over multinomials, literally the parameters of a Dirichlet priors, which go by alpha 1 through alpha k, are going to be the counts to be used. Whereas if they were all 1, the pseudo-counts, so these are the pseudo-counts. If they were all 1, this corresponds to a prior that prefers uniform, but not by much. If they were all 100, this corresponds to a prior that prefers a uniform by a lot. Now we're talking about a prior over all multinomials. So the uniform distribution is 1 point in that space. This is a prior over multinomials. So the pseudo-count method, Laplace, I don't think knew any of that. He just added 1. It turns out it works surprisingly well. In your homework assignment, you will need to, I think you play with it. Is that right? You play with how much you add? Yeah. And you will see the outcome. We don't discuss this thing there, but this is a useful thing to know. If you hear about the Dirichlet prior, you know it's a prior over multinomials. What else do I need to tell you about that? Oh, okay, not the only way to smooth your distribution. Sorry, go ahead.
K determined again?
Sorry?
K, how's K determined?
K is part of the problem definition. So it's the number of categories, the number of, it's the n of a multinomial. It's, in the case of flipping a coin, it's 2. In the case of dice, it's 6. It's number of possible outcomes. In the case of the topics, it's the number of document classification, it's the number of topics.
So how much N or V?
That's what got me in trouble. So it's not different than V. It is exactly V. The problem is that I need one extra step in the naive Bayes to equate the number of attributes with the number of... I need to basically assume that a word occurrence can occur anywhere in the document. It still means the same thing for the attribute. So this is why I kind of backed off from it. And I will come back to it, I guess, at the beginning of the next lecture. And I'll try to have a simpler, a clearer story by then. I realized that it would cloud the story. One last thing I need to add about this. This is not the only, this is a very common way of introducing smoothing, not just in the context of naive Bayes, but in general. The other competing method for introducing smoothing is called linear interpolation. And it's simply the probability that you assign to I by the linear interpolation method. You start with the probability assigned by the relative frequency method, which is number of counts over n. So maybe I'll write it. This is count of I over n. And then you use, say, the uniform, which would be here just 1 over k. And you combine them linearly. Combine them linearly meaning multiply this by some lambda, multiply this by some 1 minus lambda, where lambda is between 0 and 1. 1 minus lambda. This is the one that might give you 0. This is the one that gives you that level that you wanted. It's in some way similar, maybe even identical to the suggestion, the very first suggestion we had, which is just have a fixed number. Except it's not fixed, it's a function of lambda. The problem with this method, this is a very easy method. You don't need to invent counts. And you have only one. In the case of pseudo counts, you have a choice of where to put what counts and what size they should be. In fact, you have k parameters of the Dirichlet distribution. Here you have a single parameter, lambda. The problem is that if you fix lambda, you don't change it, you have the disadvantage that we discussed earlier, which is as you get more and more data, it doesn't overwhelm that smoothing factor. It has this constant distortion. So you can think of lambda as being made a function of the amount of data you have. Did we say n is the amount of data? Yeah. So as n goes to infinity, lambda would typically go to 1 in this case. These are the two main methods used from smoothing. This one has a Bayesian interpretation. This one doesn't quite have a Bayesian interpretation. It has a frequentist interpretation. And it goes by the name shrinkage. The reason it's called shrinkage is because this part, this component, is fixed, does not depend on the data. And therefore it has no variance. It doesn't matter as the data sample changes, this number doesn't change. This component is sensitive to the data. You get one sample, you get one answer. Tomorrow you have another sample of the same size from the same distribution, and you would still get a different value. So this has variance. It varies over all the samples. This has no variance. And we say that we linearly interpolate an estimator with variance with an estimator with low or no variance in order to reduce the variance of the combined estimator. Reduce the variance means shrink. So that's why it's called shrinkage. When we come back, I will hopefully have a cleaner explanation of applying pseudo-counts to naive Bayes.